Memory organization. Learning objectives. In this chapter, the user would learn the following in detail: ROM, RAM, hard disk, CD-Rom, cache memory direct mapping scheme, virtual memory concept, cache memory working principles, memory hierarchy, overview of memory hierarchies. The memory unit is an essential component in any digital computer since it is needed for storing programs and data. We are concerned with 5 types of memory: register memory, cache memory, main memory, disk storage, archival storage. Memory hierarchy. Overview of memory hierarchies. Register memory. Registers are the fastest type of memory, which are located internal to the processor. These elements are primarily used for temporary storage of operands, small partitions of memory, etc., and are assumed to be one word, 32 bits in length in the MIPS architecture. Cache memory. Cache is a very fast type of memory that can be external or internal to a given processor. Cache is used for temporary storage of blocks of data obtained from main memory, read operation, or created by the processor and eventually written to main memory, write operation. Main memory. Main memory is modeled as a large linear array of storage elements that is partitioned into static and dynamic storage. Main memory is used primarily for storage of data that a program produces during its execution, as well as for instruction storage. Disk storage. Disk storage is much slower than main memory, but also has much higher capacity. It has relatively long search times. We prefer not to find data primarily in disk storage, but to page the disk into main memory, where it can be searched much faster. Archival storage. Archival storage is offline storage such as a CD-ROM or magnetic tapes. This type of storage has a very long access time in comparison with disk storage and is also designed to be much less volatile than disk data. Computer memory system. Generally, computer memory system can be divided into 2 categories: internal memory and external or secondary memory. Internal memory. There are 3 types of internal memory: registers in the CPU, cache memory, and main memory, RAM or ROM. Information stored in internal memory can be accessed with greater speed by the CPU compared to external memory. Internal memories are volatile, only with exception to ROM. External memory. Memories that are separated from the main computer components. Information contained in external memory can only be accessed by the CPU through the input-output unit. Used to store information or program that has already or has yet to be executed by the CPU. Instances of external memory are hard disks, diskettes, CD-ROM, etc. All external memory is non-volatile. Memory consideration. The size of the different memory hierarchy partitions is also an important implementational consideration. Storage. Register files vary from a few hundred bytes to a few kilobytes. Modern caches vary from 64 kilobytes embedded processors to 2 megabyte large engineering workstations. Main memory ranges from 1 megabyte embedded processors to 512 megabyte desktop computers to tens of gigabytes supercomputers. Disk storage ranges from tens to thousands of gigabytes, the latter in the case of disk arrays. Archival storage can range as high as hundreds of terabytes for the storage of remote sensing image data. Access time. Access times for registers are on the order of 1 CPU clock cycle, similar to cache. Main memory takes more time, perhaps several clock cycles to tens of cycles, depending on the disparity between the memory and CPU bandwidths. Disk storage latencies are typically on the order of 5 to 10 milliseconds. Archival storage, with the exception of CD-ROM jukeboxes, takes minutes to days to access stored data. Memory hierarchy. Terminology. Hit. Data appears in some block in the upper level. Example, block X. Hit rate. The fraction of memory access found in the upper level. Hit time. Time to access the upper level, which consists of RAM access time plus time to determine hit or miss. Miss. Data needs to be retrieved from a block in the lower level, block Y. Miss rate is equal to 1 minus hit rate. Miss penalty is equal to time to replace a block in the upper level plus time to deliver the block to the processor. Hit time is much lesser than miss penalty. Typical values. Terminology. Typical values. Block line size bytes 4 to 128. Hit time cycles 1 to 4. Miss penalty 8 to 32 cycles and increasing. Access time 6 to 10 cycles. Transfer time 2 to 22 cycles. Miss rate 1% to 20%. Cache size 1 KB to 256 KB. Main memory, central storage of the computer, used to store instructions and data that are being executed, run. They are built based on semiconductor integrated circuits. Basically, they are divided into ROM and RAM. Read-only memory, ROM, acronym for read-only memory. Information in ROM can only be read, cannot be written or modified. Used to store permanent programs like Bootstrap Loader, that is, a program used to start the operation of a computer when the computer is turned on. There are various kinds of ROM. Among them are PROM, EPROM, and EEPROM. The difference is the ability to change data in them using specific methods and equipments. The following is a block diagram of a ROM with the size of 2K into N, 2K word, and the length of each word is N bit. Bootstrap Loader. The ROM portion of main memory is needed for storing an initial program called Bootstrap Loader. When computer is turned on, this initial program will be executed first. The entire user program will be executed next when OS is loaded properly. Computer startup. Since ROM is permanent, an initial program starts up a computer and executes OS instruction. This initial program is called a startup program. RAM, acronym for Random Access Memory. Information in RAM can be read and modified, write. Used to store programs and user data that is being executed, run. A kind of volatile memory, that is, the content in RAM will be wiped out if electricity supply is interrupted. It is relatively faster and can store up to some KB of information. RAM is constructed by using IC chip, which is available in two modes. Two types of RAM are static RAM and dynamic RAM. Static RAM, SRAM, made from flip-flop. Disadvantages: expensive, small storage capacity in a chip. Advantages: easier to use and faster access time, read and write cycle. It consists of number of flip-flops that store binary information. The stored information is valid as long as power is on. Dynamic RAM, DRAM. It stores binary information in the form of electric charges that are applied to capacitors. The stored charge on the capacitor tends to discharge with time, and it must be periodically recharged by refreshing this memory. Disadvantages: slower access time, harder to use because capacitors need to be charged for a certain amount of time. Advantages: cheaper and bigger storage capacity in a chip. A few improvements has been done on DRAM to improve its performance or access time, with different methods and names such as EDRAM, CD-RAM, SD-RAM, RD-RAM, etc. Block diagram for a unit chip RAM. It has 2000 words and the length of each word is N bit. External memory. External memory is also called as auxiliary memory. The most common auxiliary memory devices used in a computer system are magnetic disk and magnetic tapes. The following properties are to be considered to use a particular device: access time, transfer time, seek time. Access time. It is an average time required to reach a storage location in memory and obtain its content. Transfer time. It is required to transfer data to or from any device. Seek time. It is a time required to place a read or write head to a particular location. Auxiliary memory. Magnetic tape. A tape consists of electrical, mechanical, and electronic components to provide the part and control mechanism for that unit. It is a strip of plastic coated with magnetic recording medium. Bits are stored in several tracks and sectors, but data are read in a sequential manner. Reading forward, reading backward, erasing, inserting new contents, etc. are the operations performed with tape. Magnetic disk. It is a circular plate constructed of metal or plastic coated with magnetic material. Both sides of the disk are often used for storing data. Several disks are combined through one spindle with read or write heads are available on each surface. When disk rotates at a very high speed, when read or write heads placed in some position, data are read from that position. Bits are stored in the magnetic surface with concentric circles known as tracks. Each track is divided into a number of sectors. There are two forms of disks available: hard disk and floppy disk. Hard disk. Disks which are permanently attached in a unit and it cannot be removed by an occasional user. A hard disk consists of one or more rigid metal plates coated with a metal oxide material that allows data to be magnetically recorded on the surface of the plates. The hard disk plates spin at a high rate of speed, typically 5,400 to 7,200 revolutions per minute (RPM). Storage capacities of hard disk for personal computers range from 10 GB to 120 GB. 1 billion bytes are called a gigabyte. Floppy disk. It is a removable disk and can store only limited information. A floppy disk is a portable, inexpensive storage medium that consists of a thin, circular, flexible plastic disk with a magnetic coating enclosed in a square-shaped plastic shell. The disk storage locations are divided into pie-shaped sections called sectors. A sector is capable of holding 512 bytes of data. A typical floppy stores data on both sides and has 80 tracks on each side with 18 sectors per track. Cd-Rom. A compact disc, CD, also called an optical disc, is a flat, round, portable storage medium that is usually 4.75 inches in diameter. A Cd-Rom, read-only memory, is a compact disc that uses the same laser technology as audio CDs for recording music. In addition, it can contain other types of data such as text, graphics, and video. The capacity of a Cd-Rom is 650 megabytes of data. Cache memory. Small and fast memory between processor and main memory. Main memory blocks map to cache blocks. Replacement algorithm used to update cache blocks. A small and fast memory that is situated between the CPU and the conceptually, not physically. Reduces the difference of time of the memory cycle and the CPU processing time. The memory cycle time is the time used to fetch an instruction or data from the main memory until it is usable. With the technology available today, the processing time of CPU is faster than the memory cycle time by far. Cache memory. Hence, a memory which was called cache was introduced. It was situated between the CPU and the main memory. Example of cache memory. Cache memory. Example of cache memory. Cache memory. The operation of cache memory. Cache memory. Writing into cache memory. Writing into cache memory is discussed in the topics Locality of Reference, Cache Operation Read, Cache Operation Write, and Mapping Function. Locality of Reference. Analysis of large program has shown that references to memory at any given interval of time are considered to be few localized areas of memory. This phenomenon is known as locality of reference. That is, the active portion of the program and data is stored in cache memory if CPU wants to search the program. Locality of reference. First, it searches cache memory. If the program is not there in cache memory, it searches main memory. Most program execution time is spent on routines in which many instructions are executed repeatedly. Temporal. Recently executed instruction is likely to be executed again very soon. Spatial. Instructions in close proximity to a recently executed instruction are also likely to be executed soon. Cache operation read. Read hit. Item in cache. Read miss. Block copied from main memory to cache. Word sent to processor after copy. Word sent to processor as soon as available. Load through. Cache operation write. Write hit. Write through. Cache and main memory updated simultaneously. Write back. Only cache is updated. Dirty or modified bit. Block written back when removed from cache. Mapping functions. Example, cache memory. 2000 words, 128 blocks of 16 words each. Main memory, 64,000 words, 4,000 blocks of 16 words each. Memory address, 16 bits. Hit ratio. The performance of cache memory is frequently measured in terms of quantity called hit ratio. When the CPU refers to memory and finds the word cache, it is said to produce a hit. If the word is not found in cache, it is in main memory and it counts as a miss. The ratio of the number of hits divided by the total CPU references to memory hit plus misses is the hit ratio. Hit ratio equals number of hits divided by total CPU references. Usually it is 0 to 9. Cache memory access time equals 100 ns. Main memory access time equals 1000 ns. Hit ratio equals 0:9. Mapping. The basic characteristic of cache memory is its fast access time. Therefore, very little or low time is wasted for searching the words in the cache. The transformation of data from main memory to cache memory is known as mapping. There are three types of mapping available for main memory: associative mapping, direct mapping, and set associative mapping. Associative mapping cache. The associative memory stores both address and data. This permits any location in the memory to be accessed to find a word. Main memory block can be replaced into any cache block. Contention occurs only when cache is full. Replacement algorithm required to choose block to replace. Associative search of tags in parallel. Most flexible. Costly. Example of associative mapping cache. Direct mapping cache. The main memory location is accessed by using both tag and index field, whereas cache memory location is accessed by using index field alone. Cache block 0. Memory blocks 0, 128, 256 and so on. Cache block 1. Memory blocks 1, 129, 257 and so on. Contention may occur even when cache is not full. Replacement algorithm is trivial, simplest, very inflexible. Examples of direct mapping cache. The disadvantage of direct mapping. Two words with the same index in their address but with different tag values cannot reside in cache memory at the same time. Set associative mapping cache. A third type of cache organization called set associative mapping. Each word of cache memory can store two or more words or memory under the same index address. Each index address has two tags. When any one tag is matching, the corresponding data are read. When both the tags are different, CPU searches those addresses in main memory. Combination of direct and associative mapping. Blocks grouped into sets. Contention problem of direct mapping is eased. Replacement algorithm required to choose block to replace. Hardware cost of associative search is reduced. Cache that has k blocks per set is referred to as k-way set associative cache. Example of associative mapping cache. Mapping table. Virtual memory management system. The virtual address consists of 20 bits and physical address consists of 15 bits. Mapping is required to convert 20-bit virtual address into 15-bit physical address. To perform this mapping, a special table is used, that is, an S-page map table, PMP, or page table. This table is searched using the page number of the logical address if that page is available in that table. This table is searched using the page number of the logical address. If that page is available in that table, it generates frame number or block number, which is a starting address of the particular block. Virtual memory. The virtual memory is a memory management technique which does splitting of a program into number of pieces as well as swapping. Virtual memory. Separation of user logical memory from physical memory. Only part of the program needs to be in memory for execution. Logical address space can therefore be much larger than physical address space. Allows address spaces to be shared by several processes. Allows for a more efficient process creation. Virtual memory. Main issues in virtual memory design. Address mapping. How to translate virtual addresses to physical addresses. Placement. Where to place a portion of virtual memory needed by process. Replacement. Which portion of virtual memory to remove when space is needed. Load control. How much of virtual memory to load at any one time. Sharing. How can processes share portions of their virtual memory? Virtual memory concept. Virtual address or logical address, 20 bits. An address generated by the CPU is known as logical address and it is of 20 bits. Logical address is divided into two parts, page number, offset. Physical address, 15 bits. An address which is understandable by the memory management unit is known as physical address and it is of 15 bits. It is divided into two parts, frame number or block number, offset. Address space and memory space. An address used by a programmer will be called a virtual address and the set of such addresses the address space. An address in main memory is called a location or physical address. The set of such locations is called the memory space. For example, consider a computer with a main memory capacity of 32K words, K equals 1024. 15 bits are needed to specify a physical address in memory since 32K equals 215. Computer has available auxiliary memory for storing 220, which equals 1024K words. The auxiliary memory has a capacity for storing information equivalent to the capacity of 32 main memories. It denotes the address space by N and the memory space by M. We then have for this example N equals 1024K and M equals 32K. Block diagram for virtual memory concept. Virtual memory concept. In a multi-programming computer system, programs and data are transferred to and from auxiliary memory and main memory based on demands imposed by the CPU. Suppose that Program 1 is currently being executed in the CPU. Program 1 and a portion of its associated data are moved from auxiliary memory into main memory as shown in the page before. Virtual memory implementation. Paging. Segmentation. Combination of both. Paging. Paging is a memory management technique that permits a program's memory to be non-contiguous into physical memory, thus allowing a program to be allocated physical memory wherever it is possible. The term page refers to groups of address space of the same size. Address space and memory space are each divided into groups of fixed size. The physical memory is broken down into groups of equal size called blocks, which may range from 64 to 4096 words each. Address mapping using pages. The physical memory is conceptually divided into a number of fixed size blocks called frames or page frames. The virtual address space or logical memory of a process is also broken into blocks of the same size called pages. When a program is to be run, its pages are loaded into any frame from the disks. Example, consider a computer with an address space of 8K and a memory space of 4K. Paging. Disadvantage of paging. Problem with this approach is memory access time. Memory is slowed by two factors. One for page map table. One for the data. Virtual memory implementation. Memory mapping table in a paged system. The memory page table consists of 8 words, one for each page. The address in the page table denotes the page number and the content of the word gives the block number where that page number is stored in main memory. The table shows that pages 1, 2, 5 and 6 are now available in main memory in blocks 3, 0, 1 and 2 respectively. A presence bit in each location indicates whether the page has been transferred from auxiliary memory into main memory. A 0 in the presence bit indicates that this page is not available in main memory. Virtual memory implementation. Associative memory page table. Instead of using page table to map page number into block number, associative memory page table is used for the same purpose. The page number and offset is kept in a special register called argument register. The key register is used to set a particular bit to 1 to denote that information is searched in the associative memory. If a match is found, associative memory generates a block number by combining with offset to find the physical address. Advantage. A set of associative registers are built of high-speed memory. Associative memory page table. Virtual memory implementation. Segmenting. A segment is a set of logically related instructions or data elements associated with a given name. That is, programmer thinks of their programs as a collection of logically related entities. Segments may be generated by the programmer or by the operating system. Examples of segments are a subroutine, an array of data, a table of symbols, or a user's program. The address generated by a segmented program is called a logical address. This is similar to a virtual address except that logical address space is associated with variable length segments rather than fixed length pages. Segmented page mapping. The logical address shown is partitioned into 3 fields. The segment field specifies a segment number. The page field specifies the page within the segment and the word field gives the specific word within the page. A page field of k bits can specify up to 2k pages. A segment number may be associated with just one page or with as many as 2K pages. Segmented page mapping. In case of a memory reference from the CPU, it will require 3 accesses to memory. One from the segment table, one from the page table, and the third from the main memory. To avoid this speed penalty, a fast associative memory is used to hold the most recently referenced table entries. This type of memory is sometimes called a translation look-aside buffer, TLB. Segmenting. Mapping in Segmented Page Memory Management Unit. Segmented page mapping. Numerical example. Consider the 20-bit logical address specified in figure. The 4-bit segment number specifies one of the 16 possible segments. The 8-bit page number can specify up to 256 pages, and the 8-bit word implies a page size of 256. The physical memory shown in figure consists of 220 words of 32 bits each. The 20-bit address is divided into 2 fields, a 12-bit block number and an 8-bit word number. Thus, physical memory is divided into 4096 blocks of 256 words each. A page in a logical address has a corresponding block in physical memory. Segmenting. Segmented page mapping. Numerical example. Consider a program loaded into memory that requires 5 pages. The operating system may assign to this program segment 6 and pages 0 through 4 as shown. The total logical address range for the program is from hexadecimal 60,000 to 604FF. When the program is loaded into physical memory, it is distributed among 5 blocks in physical memory where the operating system finds empty spaces. Numerical example. Now, consider the specific logical address given in figure. The 20-bit address is listed as a 5-digit hexadecimal number. It refers to word number 7E of page 2 in segment 6. The base of segment 6 in the page table is at address 35. Segment 6 has associated with it 5 pages, as shown in the page table at addresses 35 through 39. Page 2 of segment 6 is at address 35 plus 2, which equals 37. The physical memory block is found in the page table to be 019. Word 7E in block 19 gives the 20-bit physical address 0197E. Note that page 0 of segment 6 maps into block 12 and page 1 maps into block 0. Logical to physical memory mapping. Logical to physical memory mapping. All numbers are in hexadecimal. Segmentation. Advantages. As opposed to paging, no internal fragmentation, but external fragmentation. May save memory if segments are very small and should not be combined into one page. Example, for reasons of protection. Segment tables. Only one entry per actual segment as opposed to one per page in VM. Average segment size is greater than average page size, which is greater than or equal to less overhead, smaller tables. Disadvantages. External fragmentation, costly memory management algorithms. Segmentation, find free memory area big enough. Search. Paging, keep list of free pages, any page is okay. Take first. Segments of unequal size not suited as well for swapping. Working principles of cache memory. The principle of locality. Program access a relatively small portion of the address space at any instant of time. Example, 90% of time in 10% of the code. Two different types of locality. Temporal locality, locality in time. If an item is referenced, it will tend to be referenced again soon. Spatial locality, locality in space. If an item is referenced, items whose addresses are close by tend to be referenced soon. Principles of operation. At any given time, data is copied between only two adjacent levels. Upper level, cache, the one closer to the processor. Smaller, faster, and uses more expensive technology. Lower level, memory, the one further away from the processor. Bigger, slower, and uses less expensive technology. Block, the minimum unit of information that can either be present or not present in the two-level hierarchy. Conclusion. In this chapter, we have covered the following aspects of memory organization: ROM, RAM, hard disk, CD-Rom, cache memory direct mapping scheme, virtual memory concept, cache memory working principles,